A cylinder-shaped can needs to be constructed to hold 300 cubic centimeters of soup. The material for the sides of the can costs 4 cents per square centimeter. The material for the top and bottom of the can needs to be thicker and costs 5 cents per square centimeter. We want to find the dimensions for the can that will minimize the production cost. So the first thing we should recognize about this problem is that the volume of the can, or the right circular cylinder, must be 300 cubic centimeters. And since the volume of a cylinder is equal to pi r squared h, for this problem, pi r squared h must equal 300 cubic centimeters. And this is called the constraint. Next, the cost function involves the surface area of the cylinder, as well as different costs for the top, bottom, and side of the can. So let's first talk about the surface area of our cylinder. If you can imagine cutting out the top and bottom of the can, and then slicing the side and unrolling the side, hopefully you can visualize that it would look something like this, where this would be the top and the bottom, and this would be the side of the can. Notice how the radius for the two circles and the cylinder would be the same. The height of the can would give us this length of the rectangle. And then this length here is a little tricky. This actually comes from the circumference of the circle here. And the formula for the circumference of a circle is equal to 2 pi r. And again, remember the cost for the top and bottom is 5 cents per square centimeter. And the cost for the side is 4 cents per square centimeter. So with this information, we can write the cost equation. The cost is going to be equal to 5 cents times the area of the two circles. Well, the area of a circle is equal to pi r squared, so we'd have times 2 pi r squared plus 4 cents times the area of the rectangle, which would be 2 pi r h. So let's go ahead and take this cost equation back to the previous slide. Remember, our goal here is to minimize the cost, but we want the cost function in terms of one variable. Right now it's in terms of two variables, both r and h. So what we'll do now is use the constraint to perform a substitution so that we can obtain the cost function in terms of just r. To do this, we're going to solve the constraint for h, so we're going to divide both sides of this equation by pi r squared. So h is equal to 300 divided by pi r squared. And now we can substitute this quotient here for h in our cost equation. So we would have c equals 0.05 times 2 is 0.1. So we have 0.1 pi r squared plus 0.04 times 2 would be 0.08 pi times r times h. But again, h is equal to 300 divided by pi r squared. Now let's go ahead and simplify this product here. Pi over pi would simplify to 1. Notice one factor of r would simplify as well. This would simplify to 1. This would simplify to r to the first. So now we have the cost function in terms of r. We have c equals 0.1 pi r squared plus 0.08 times 300 is 24. So we have 24 divided by r, which we can also write as 24 r to the power of negative 1. Remember, if we move r up into the numerator or across the fraction bar, it's going to change the sign of the exponent. So now that we have our cost function in terms of r, to minimize c, we'll find the critical numbers by determining where the first derivative is equal to 0 or undefined, and then from there we'll determine which value of r minimizes the cost. So c prime, which will be the derivative with respect to r, would be 0.2 pi times r to the first, or just r. And here we're going to multiply by negative 1, so we'll have minus 24 r to the power of negative 1 minus 1, or negative 2. Let's go and take this derivative function to the next slide to determine where it's undefined or equal to 0. Let's go ahead and rewrite this as a fraction. We can write this as 0.2 pi r minus 24 divided by r squared equals 0. Now we can see it's going to be undefined when r equals 0, but we know the radius can't equal 0. Therefore, we'll just go ahead and solve this for r by multiplying both sides of the equation by r squared. So on the left side, we're going to have 0.2 pi r cubed. Notice how the r squareds will simplify out, so we'll have minus 24 equals 0. We'll go ahead and solve this for r cubed, so we'll add 24 to both sides. We'll go ahead and divide by 0.2 pi. So we have r cubed equals 24 divided by 0.2 pi. Now to solve for r, we'll take the cube root of both sides of the equation. To save some time, I've already determined this value. We have r is approximately equal to 3.3678. Now because we only have one critical number, we probably would be okay by assuming this value of r is going to minimize the production cost. But just to be sure, we should use either the first or second derivative test to make sure we do have a minimum value at this value of r. Let's go and use the second derivative test. So if here's the first derivative, then we can find the second derivative. Applying the power rule here, we would just have 0.2 pi. Then we multiply by negative 2, so that's going to be plus 48 times r to the power of negative 3, which is the same as dividing by r to the third. Now notice if we substituted 3.3678 for r, this sum would be positive, so c double prime of 3.3678 would be greater than 0, which means the function would be concave up, which is good news because if the function is concave up at this critical number, that means we'd have a minimum function value, or in this case, a minimum production cost. Going back to the problem just for a moment, we're trying to find the dimensions that will minimize the cost, so we just found the radius that will minimize the cost, but we still have to find the height of the cylinder that would minimize the cost, and we can do that using this equation here, since we know h must equal 300 divided by pi r squared. So let's go ahead and finish by doing that. So that means h is equal to 300 divided by pi times 3.3678 to the second power. Again, to save some time, I've already determined this value. H comes out to approximately 8.4194 centimeters. So we know the production cost under these conditions is minimized if the can has a radius of 3.3678 centimeters and a height of approximately 8.4194 centimeters. Now, of course, if any of the conditions change, for example, if the volume changes, or if the cost for the side or the tops of the can change, the dimensions of the can that would minimize the production costs would also change. I hope you found this explanation helpful.